Okay, folks, we will be talking about distributed forces, centroids, centers of gravity. So why don't we worry about how forces are distributed? Well, okay, so previously we've been talking about point loads, concentrated loads, so on and so forth. The problem with those is that they're not a real thing. Anytime you have some sort of force, it is going to be distributed over an area. Even if I take my pen here and jab it into my hand, that force is being concentrated into a very small section of my skin, but it is distributed over that area, even if the area is small. Probably the closest thing that we get to an actual point load would be, say, the force of gravity on a particle. Not even on a molecule, not even on an atom. If you get the force of gravity on a proton or the force of gravity on a neutron, then that I think would be a point load. But again, that's not really all that useful. So we often find it easy and convenient to do our math if we represent various distributed loads as point loads. And the way we do that is basically figure out what the total force of that load is and find out where we can place it such that there wouldn't be an equivalent moment. So I think most of you are probably familiar with the concept of a center of gravity. So essentially, gravity exerts a force on each particle in a body. And if you take up all the sums of those forces on all those particles, you get the weight of the object. But you're also going to get what we call a center of gravity, and that's basically taking up all of the little individual components. Instead of this thing with a large mass, instead we look at all the tiny little forces from gravity of each individual particle, each individual little block. We kind of add all those up. We add all those up, and essentially, when we add up all those tiny little bits from each particle, we get the total mass, but we also get a location at which it acts. So it acts at the center of gravity. And essentially what we're saying there is if we take the moment of all of these individual forces that make up the total weight of the object, if we take all of those billions of little moments, take all those billions of little forces and take a moment about the center of gravity, then that moment will be zero. It'll all add up zero, regardless of kind of the orientation of the object. So that's a physical location in an object, or sometimes it's not necessarily within an object, but in relation to an object. For example, the center of gravity of this ring, my wedding ring here, it's located in the middle of the empty space inside the ring, but it's in relation to the object itself. So anyways, we can add all those up and pretend that the weight of the object is a single force acting through that point. And then we can do stuff like, say, balance the thing on a pencil as long as the pencil is placed at the center of gravity. It'll be in equilibrium at that point. So the annoying math. So basically, for a 2D body, what we want to do is, if we take our object and split it up into a whole bunch of tiny little cubes, what we can do is we can find the centroid of the object times the weight of the object is going to be equal to, oh, I realized that top of that got cut off there. It's going to be equal to the integral of, the integral of x times the tiny little cube of weight. So we're breaking up this thing into tiny little cubes, multiplying each of those cubes by its distance from the y-axis, and then adding all of those up in an integral. So that's this is what we call the first moment of area, with regards to y here. So that if we're talking an object that has a uniform density, then essentially this becomes we basically, and if we're talking a plate, then the thickness, the weight is going to be equal to the volume of the object times its density. So we can break the volume up into its thickness and its area. We can kind of just factor out the thickness and the density portions, because those kind of assuming that if we're talking a 2D body, then those don't vary at all. So this becomes a matter of the area, and it becomes a geometric function. So that allows us to get the first moment of area. So we can do that we can get our x bar a or our y bar a. That'll be our first moment area with regards to y, or first moment area with regards to x. And we can do something similar to we can do something similar if we're working with not a plate, but some sort of a wire. We can break it up into chunks of length instead of chunks of we can break that weight up into chunks of length, and instead we kind of treat it. In either case, we can kind of treat it as if we're only worried about the area, or only worried about the length. So we can. This is essentially us taking the previous page and making the assumption that this object is perfectly flat and has uniform density. So then we're worried about the centroid of this area, and essentially once we kind of do this calculation, we can find the location of the centroid by dividing by the area. Similar idea for the line. Same idea. We're just worrying about the line itself. We're worrying about the length of the individual length components of the line, and the x locations at that point. Same here with the y. And then do that integral, divide by the total area, we get our location of the centroid. Same deal with y. Is it up a little bit there? Okay, so here we've got a few common centroids. Here, I think I zoomed it. There we go. I zoomed in a bit too much, didn't I? Okay, so some common centroids. Stole this from your textbook, except for one thing I had to add myself. The location, the x location of a of a triangle is just basically taken from any point. It's just the it's the average of the x of the location along the x-axis of each of the corners. I don't know why they didn't include that in your textbook. Feel free to go ahead and add that. That'd be great. To the end, just x1, x2, x3 divide by 3. So again, if we've got a right triangle, it's just located at 1/3 the distance of the base here, because basically that's us using this the right the 90-degree angle as the 0, and then so 0 plus 0 plus b for our base divided by 3 gets us b over 3. Same deal with the height. The y bar location works out to the same thing as long as the bottom base here is flat. And then here's some others. One thing you'll notice that you should be able to notice is that anytime an object has an axis of symmetry, then the centroid is on that axis of symmetry. And that's basically us. If you want to know how that works mathematically, that's basically saying that when you take when you take your individual moments on either side, as they cancel out when taken about this axis. So if you've got one axis of symmetry, the centroid needs to be on that axis of symmetry. If you have two or more axes of symmetry, then the centroid is located at the intersection of those axes of symmetry. So, just a few other centroids you might be worried about. Arc of a circle, semicircular section, so on and so forth. So again, these ones are used for area. This one's used for area too. These ones could be used to calculate centroids of lines. And I guess they didn't bother to include rectangles, because I think it should be fairly obvious that the centroid of a rectangle is directly in the middle of the rectangle. So what we can do is we can, instead of necessarily having to do annoying integrals for annoying shapes, what we can do is we can basically, if we already know what the, if we already have shapes that we can determine, then we can figure out what the total first moment of area for those for the combination of those shapes would be by adding each of the individual components of their first moments of area together. Then once we have that, we can find our x bar, which is just the location of the centroid for the composite thing, by taking this, dividing by this, and that's how we get that. So let's do an example for that. So we're going to be doing this one to start. So we have a plane area shown, and we want to determine the first moments with respect to the x and y axes and the location of the centroid. Let's pull up OneNote here. I'm going to copy and paste that. No, I kind of cut that off, didn't I? Let's do better. So, and one thing to keep in mind is that if you're adding sections together, you can add it, but you can also take the you can also basically subtract from sections as well. So we've got this thing here. We want to break it up into its component shapes and kind of determine what we're going to add and subtract in order to give us our give us our centroid. So essentially, what I think we should do is we should take a rectangle like this. That's going to be our base shape. And we're going to subtract from it. I'm going to use fuchsia here to kind of show the areas I'm subtracting. I'm going to subtract from it this triangle here. We're going to add to it this semicircle here. And then we're going to subtract from both those things this circle here. So that overall should give us kind of where we're going from. So well, let's see how let's figure out where we're working from for that. So to start off, we'll start with our X bars for that. So first off, we have. I'm gonna change things up a little bit, just because I think it makes the math a bit easier. I'm gonna define our origin here. So at the very bottom right corner, sorry, very bottom left corner. I'm just going to call that X prime plus to indicate that I kind of shifted it. So first things first, we have this rectangle here. So we want the X bar times the area of that rectangle. So the X bar times the area of that rectangle. So the area is going to be 140 millimeters times this distance. The width of the overall thing is 120 millimeters. And measured from this corner here, the X bar location, so the centroid of just that rectangle, that's going to be half of the 140 millimeters, so it'll be 70 millimeters. So we'll call that, that's the X bar area for 1. The next section that we are going to do, let's do this semicircle, because that's the other thing we're adding. So we'll call that 2. I'm going to switch to blue for that. Okay, so again, area. So area for a semicircle, that's just going to be pi over 2 times the radius squared. So in this instance, the radius is 60 millimeters. I'll go ahead and erase our radius squared there, put in 60 millimeters. And then we also have our X bar location. So we first off, we know it's going to be above this 140 millimeters. So we'll go ahead and throw the 140 millimeters in there. And then I'll just go ahead and have a glance at our graph here. So we've got a semicircular area here, and its Y bar location is given here as 4 thirds r over pi, or 4r over 3 pi. So times 4r, so 160 millimeters over 3 pi. Oh, and I realize that's not times, that should be plus. Let's plus that there. So what does that give us? All right, pi over 2 times 60 millimeters squared. So this term here that one's 5,655 millimeters squared. And then this term here, 140 plus 4 times 60 divided by 3 pi. That totals to 165.5 millimeters. So that's given us a 939,704 millimeters cubed. All right, and I guess I should actually calculate what our one value there is. For 140 times 120 times 70. All right, so we got 1,176,000 again millimeters cubed. Okay, so we got that. The next one that we're going to want to be taken care of is probably, well, let's do the circle itself. So we got the circle itself. So X bar A three. So that one is going to be area of the circles, pi times its r squared. So our radius there is 40 millimeters. Nope. And then times the x bar for that, which is going to be 140 millimeters. So pi times 40 millimeters is 5,024 millimeters squared times our 140. That gives us 703,360 millimeters squared. And next up, we have our third little law, our second thing to subtract, our little triangle there. So, area of that's just going to be the base times the height divided by 2. So 60 times 120 divided by 2. And then the X bar location of that's 1/3. So we're starting from the fat end, going to the pointy tip. So that's going to be 1/3 of the height. So that'll be 20 millimeters. So our 60 times 120 divided by 2, that's going to be 3,600 millimeters squared times 20 gives us 72,000 millimeters cubed. Okay, so now we just need to add those values up. So that's 72,000 plus 703,000 plus 936,000 plus 1,173,000 gives us 'Okay, so the sum of our xi AIs, that is 2,887 millimeters cubed. And then just to get our X bar location, that's just going to be equal to that divided by our total area. So our total area, all right, so we got that much. We've got this much. We've got that much. And we've got this value, which I didn't bother to calculate yet, so 140 times 120. That's equal to 16,800. So, total area. Total area there is going to be 31,000 79 millimeters squared. So our X bar total, 2,887,000 millimeters. I wrote squared there, didn't I? Cubed. Millimeters cubed divided by our 31,079 millimeters squared. That gives us an X bar of 92.9 millimeters. Nope. 9. So that's telling us that measured from this corner, our center of gravity should be located, I guess probably right about here. No, right about here. Okay, so that is that for the X bar. Now we also need to look at our Y bar. So I'm gonna be tricky about things. So we can make things easier by readjusting our coordinate system. So essentially, just let me go and I'm gonna recopy our problem, so I get a nice clean graph. So recopying the problem, essentially, if we were to find the coordinate system that we're measuring with, kind of straight down the middle here, then when we go to take the add up the when we add up our Y bar components, or Y bar A components, basically the Y bar ends up being 0 for everything but this triangle, because we are because the centroid of the circle here, that's going to be right here. The centroid of the semicircle, also located on the axis. The centroid of the rectangle we're starting with, that's also going to be located on that axis. So essentially, that just means that when we do this, the only term we end up with is the let's see here. I'm going to just erase that, and I'm going to put a little triangle. Oh. Is the Y bar for the Y bar for the triangle times the area of the triangle. So that's simple enough to get. So basically, we know that measured from this corner, it would be 2/3 of the way across. So from here to here is 40. Oh wait, no, 2/3 of 80. From there to there is 80. There's our Y bar. Or from here to here is 40, either way. So we know that if we want to figure out what this distance is, that's just going to be this distance here, this 80, minus half of our 120. So 80 minus 60 gives us our y bar relative to this axis, relative to the new centered y-axis. So that's just going to be equal to 20. So the y bar for the triangle times its area, that's just going to be equal to 20 times, what do we say the area for the triangle was? That'll be 3,600. Meter squared. I forgot to throw the millimeters in there. So 3,600 times 20 millimeters. That is 7,200, which I guess isn't all that surprising. It's the same value we got from here. We're kind of doing the similar thing. Anyways, so that gives us the that's the total of these components for our y bar. So our overall y bar is just going to be equal to 7,200 millimeters cubed. It's cubed, not squared, divided by the total area of the thing. So the total area of the thing, that's, we already added that up. That's the 31,079 millimeters squared. So 72,000 divided by 3109. That just gives us a y bar of 2.3 millimeters, which is not much, but that really shouldn't be surprising, considering that so much of the component is kind of centered about that one axis. So there's only going to be a slight shift. So that'll be located, yeah. This is probably a bit more than it is actually, but 2.3 millimeters to the side from there. And again, we're located at about 32.9 millimeters up from here. So about there. About there will be our centroid. So redefining this in terms of the original coordinate system that we're given, because that's, if someone gives you a coordinate system with a problem, they're going to want the answer back in terms of that coordinate system. So do that. So basically that allows us to say, okay, so we've got our x bar here. Our x bar is just going to be that distance there. So measured from down here, it was 92.9. So subtract the 60 millimeters from that. So our x bar is going to be, why am I starting to write 9 again? 39.2 millimeters. And then our y bar from there to there, that's going to be the 2.3 millimeters plus half the width, so 60. So y bar is equal to 62.3 millimeters. And that is, let's I just go double checked. So yeah, yep, there we go. So we got our first moments of inertia that we solved for. That's that value there and this value here, and then we used it to solve for our centroid with respect to the axes in question.